Welcome, everyone. We're going to begin the webinar today on aluminum versus steel. I'm Melissa Jolls with RDA Impact, and Ken Boylan, Global Training Manager of Chief Automotive Technologies, is your presenter for this webinar. The presentation should take approximately 45 minutes, and we are recording it. We'll post it on our YouTube channel. If you have any questions, feel free to type those in the chat box at the bottom right of your screen, and Ken will answer those throughout the presentation. And we'd like to know how many people are attending the webinar today. So if you have more than one person watching the presentation with you, if you could type the number in the chat box and send that to me, we'd really appreciate that. All right, now I'm going to turn it over to Ken.
Thank you, Melissa. Good day, everyone. Thanks for the opportunity to speak here. It's a real privilege. I represent Chief Automotive Technologies. We are part of Chief University and put together a little program here. Hopefully we can get it to work here in 1 second. Oh boy, Melissa, this is not good. Oh, here we go. Sorry about that, folks. Hopefully this will hold together for us. We're going to be talking today about a lot of different topics, and I know the main topic for that was going to be steel and aluminum, and surely we'll talk about that in detail, along with some of the other industry challenges that we're facing in the industry today. Just have to bring that in. So we're going to kind of talk about material innovations, vehicle construction methods, whether it's steel, aluminum, maybe a little carbon fiber. But the other thing that's changed with that are the joining technologies that have evolved due to the advanced eye-strength steels and so forth. So this really is about technology, about quality, about precision. We'll talk about a little bit of welding and how all of those things affect the vehicle. We're certainly not dealing with the same vehicle that we were 10, 15 years ago, or in many cases even 2 or 3 years ago. And that's just how fast technology is changing. So I kind of like this idea when the self-driving car is there, you kind of relax, take a break, let the car do the driving. You got a little sink there, and a toilet, and everything that the guy needs, even with a guitar. So you could probably relax and come to work very refreshed, ready to go. Who knows? But in order for that all to happen, this is what the vehicle is going to have to look like with all of this technology involved. Now, we don't see stuff sticking out of the car like that on modern vehicles, but that's installed somewhere on the vehicle so they can perform all the functions that are needed for safe driving and some of the things that go along with that. You know, when we talk about vehicle construction, there are so many technical advances coming our way. It's actually just too fast for the technician and really can't hardly hold on to what some of these changes are in our industry. We're dealing with different materials all the time: aluminum, carbon fiber, advanced high-strength steel, magnesium, composites, all kinds of different things. And all of that goes into not only the vehicle structure and strength, but add all of the things that we just looked at about blind protection, spot protection, parking assist, brake assist, all the other things that go along with the vehicle. And as you know, it becomes a complicated thing. Well, why do we have these changes? Because of the corporate average fuel economy, the federal government mandates that vehicle manufacturers get 54.5 miles per gallon by 2025. We're not quite there yet, folks. But that's why we're seeing all these changes. You know, vehicle manufacturers I deal with frequently, and you hear the sound from them that says a gram a day. And what that means to them is they can reduce the gram of weight from the vehicle every day. They are succeeding in getting better fuel economy. The lighter the vehicle, the better the fuel economy. So we see a combination of a lot of materials, and the question always comes up, well, which one's going to win out? Aluminum, steel, carbon fiber, magnesium? I really can't tell you, but I do know this. You're seeing all of those in all kinds of vehicles. So I don't know that we're going to see one predominant material. I'm going to assume that with technology and it changes, the normal vehicle will have 3, 4, 5, 6, 7 types of materials. Well, every time a vehicle construction changes, it changes how we repair the vehicle. And what we have to do is stay up with the industry. That is a tall task for everyone. I recall working in the body shop in the back of the dealership, probably the last person to ever know of any of the changes that happened on the vehicle. Didn't have access to OEM information, didn't get formal training. So we just fixed the car the way the guy in the stall next to us did. not knowing that was the right way or not. So what do we need? We need solutions. We need to know that what we're doing to repair the vehicle is correct. And OEM repair information supersedes anybody. I work for Chief and have since 1986. I've also taught ICAR classes for 25 plus years, and it really doesn't matter what Chief or ICAR says. It's what the OEM says. They're the ones that call how they want their vehicle repaired. So looking at education, how do you get there? I don't know. You just have to keep going, have to keep trying to be educated. And it takes an effort. I'm sure that people today realize that if you want to be doing this kind of work the next 3 to 5, 10 years, training is going to be required. And it's not just training. You know, we think about training. We don't act on it all the time because we don't have a formal plan of how we go about understanding what our training needs are. So you can kind of look at this little chart, and you see on some of the business objectives, the customer's needs, what that person's need, what the need of the shop is, the technology and the changes. All of that becomes part of a learning needs assessment. And I guess as an industry, we're not real used to doing something like that. But the better trained your people are, the better they will perform, the better you'll have a good repair, safe repair when you deliver the vehicle. Nothing's worse than kind of hanging your head when you deliver the vehicle knowing that something isn't what it should be. For those of us that have been in this business for a long time, we have to take ownership of being a lead technician, being a trainer, being a coach, helping those that are on their way into the industry with personal development. I happen to be working at a shop where we're doing some training. They have 3 apprentices. Each technician has his own apprentice that he teaches, he coaches. He's ensuring their personal development, they get the right tools, they're going to the right classes. Folks, that's what it's going to take for our industry, are the right people to fix these cars correctly. Work safety, obviously we're dealing with a lot more technology than we have in the past. We'll kind of skip that for today, but a good topic. You know, they just don't make cars like they used to. I like to play this little video because it's kind of fun if it'll play for me. Let's see. Whoops. Sorry, folks. This is more embarrassing for me than you know. We'll get back up there in a second. I'm sorry. Hope I didn't make you too dizzy. Well, certainly my little video is not going to work, so that tells me that the one at the end is not going to work. But you know, you kind of talk about the evolution of the vehicle. We've come a long ways from assembling vehicles like you see here on an assembly line. All the way through the early 30s and the 40s, and then getting into the 50s, we saw the changes in the technology in vehicles. Every time a vehicle construction changes, so does the method of how we repair it. How they build the vehicle has become really high tech, as you see here. As you notice there, it's pretty high tech, how vehicles are built. So the construction of the vehicle has changed drastically. And I brought this little photo up here just to kind of show you one of the things that's real critical on advanced high-strength steel vehicles, which is where we'll start with this. You know, all of us have looked under a unitized body vehicle before and seen where the frame rails are like this or like this, and then they just disappear. When you look at a late model vehicle, you see something different than what we had in the past. And it is this right here. It's another subrail. It goes out, and if you look at it, it goes right out into the rocker panel. So on what we've experienced on a hard front end hit, we see things that we haven't seen before. A vehicle runs into a wall at 35 miles an hour. You can still open and close the door. Not even a buckle in the roof. Where did the damage go? It's a great question. In our classes, we used to call that collision theory. We thought we knew where the damages were going to deflect through the vehicle. We no longer call that a theory because it's actually a dynamic that's built into the vehicle. The engineers that build vehicles call that load pathing. We don't use that term very much in the industry these days, but it's becoming very, very critical that we understand what load pathing means. It means as the vehicle collapses during a collision, the forces are distributed through pinch welds. I'm sorry, through spot welds, not pinch welds, through spot welds. And through spot welds to a place where there's a reinforcement where the forces may be directed to the side, to the rear, or down. That's why we call it dynamics, because it's built into exactly how the vehicle will react in a collision. See a front-end hit on a late model vehicle like you're looking at here on the lower right, you could have a buckle in the rocker panel. We've never seen that before. That energy is distributed differently than it has in the past. Yes, the entire vehicle is built around passenger safety and the center section. Where will you find all of the advanced high-strength steels? You're right, mostly in the center section. It's pretty easy to talk about high-strength steels, and we'll get into that in a moment, because we need to know one thing. Where are they? Right? If we know where they are, then we'll start to look and understand how can we do any repair. I can give you the whole class that we teach on advanced high-strength steel in 4 words. You can't repair it, period. Not one manufacturer allows a repair, sectioning, heating, straightening of any advanced high-strength steel panel with very, very few exceptions. So we need to be aware of these techniques. I go into shops all the time and I see someone cutting a B-pillar that is advanced high-strength steel and trying to weld it with a MIG welder. Folks, it will not work. That weld will not be the quality that it needs to be. An advanced high-strength steel panel needs to be attached at its joining location. No sectioning allowed. I guess I'm a little passionate because I see this thing happen, and the thing that bothers me when I look at it is airbag timing. You know, the airbag has to deploy at about 7/10 of a second, right? But the collision, actually the airbag has to deploy before the collision's over in about 3/100ths of a second, because it has to go off before the passenger goes all the way forward. And if we were to change how we welded something together, or if we sectioned something, or if we heated something, do you think that would affect airbag timing? Absolutely. I'm convinced that at some point in time our industry will face some challenges of not returning a vehicle to not pre-accident condition. That doesn't exist. The right word is the correct load path vehicle that will react exactly the way the manufacturer designed it to react in the next collision. That's a tall order for us. That means we have to pay a lot of attention to detail to return the vehicle to its pre-accident crash rating. Tall order for us. So efficiently, things like we saw in the past where we could do an A-pillar, and maybe you could section it in the past. If you look at this yellow piece, it's not repairable, not sectionable, so you can't even section these components. It becomes a real problem. You know, vehicle manufacturers are changing technology so fast, it's almost hard to stay up with. Now, what I'm showing you on the screen here is a design that BMW played with that is an A-pillar. And on this A-pillar, what you will see is it's very large in the beginning of it here. I'm sorry, it's very kind of backwards. It's small at the beginning. And the reason the manufacturer would want to make that smaller is for the blind spot that so you can't see around the A-pillar. So if they make that smaller, you have a better line of sight. This A-pillar that you're looking at here is made of folded metal that upon impact expands to this size of the original type of A-pillar. Folks, that's something we've never seen before. It's not on the market yet. It may be. Lord help us if we try to cut through that A-pillar. Who knows what kind of damages we'd occur with that. We just need to know how to fix them. I'm convinced that we can fix just about anything We just need to know how and make sure that it's a recommended procedure by the manufacturers. They certainly don't build vehicles like they do. Excuse me. I want to spend a couple of minutes on steel. Steels indeed are awesome. I don't know, I get excited when I'm around steel. I'm sure somebody else out there has been like that. I remember when I went through Bethlehem Steel the first time, I could not sleep at night. Something wrong with me, I know. But I want to click on this a little bit here and talk about steels. Bring this one up and over. And as you look at the screen here, what we have here are various types of steel. And these are not all of the high-strength steels or mild steel families that you would see, but only a few. But I put these on the screen to make a really good illustration of what's happened with steel. And not only that, where are we going with steel? I don't think they're done making developments. You know that 80% of the steels on the market today have been developed in the last 15 years. That's a huge amount of development and a huge amount of change. You know, when I started working on vehicles, they were all this mild steel. And if you look at that picture under microscope, you can see the grain structures, what that's showing. And the grain structure is kind of spread apart. So for mild steel to get strong, it needs bulk, thickness. You know, one of the ways that we measure steel, the strength of steel, is a yields test. So if you were to take that piece of mild steel, grab onto it on each side and pull it apart, it would take approximately 30,000 pounds of pressure to pull that piece of steel apart. Now that sounds like a lot of pressure. But now we're dealing with bulk. And in the 70s, when the corporate average fuel economy was first made by the government to increase vehicle mileage, the manufacturer had to rethink about steel. That's when the HSLA steel started coming out. And what you see with that is a much tighter grain structure. The tighter the grain structure, the stronger that steel will be. In this case, with a yield strength of 70,000 pounds approximately per square inch of pressure to pull high-strength steel apart. Now, some people aren't even aware of this, but you need to kind of research what you can and cannot do with high-strength steel, HSLA, the steels that we had in the past, where they had guidelines. As an example, the Chrysler in the past was 750 degrees for 2 minutes. GM is 90 seconds, I think, for 1 minute or something like that for 1,000 degrees. Folks, when you get up in that temperature of high-strength steel, the fear of the manufacturer is when you get above those temperatures, the alloys start to dissipate and the molecules start to separate. And guess what happens? It reverts to mild steel. So if you overheat an area of high-strength steel and it reverts to a mild steel, obviously, will it react the same way in the next collision? I guarantee it won't. I was a portion of a lawsuit that actually an airbag deployed what I thought was too quick. There's too much damage on a vehicle, on a Mercedes. We did a yield strength test because it was going to court. Cut a piece of the steel, pulled it apart. It had been overheated. Used a little borescope to see on the inside of the rail. The next call was to the shop. Guess what? They had the liability for that. So we live in a very difficult situation here. We need to know how to repair these vehicles and apply the skills necessary. We haven't even got to the advanced high-strength steels. Now, there's a lot of confusion, or some confusion, I should say, about advanced high-strength steels. And I've done a little bit of research, because there's a bunch of different high-strength steels. As you can see, there's complex steels, baked hardened dual-phase, hot-formed, trip steels, TWIP steels, all of these others. The one thing that is common to all advanced high-strength steels is this. They are warmed up to a specific temperature, suspended at that temperature, and then they're alloyed. And then they're cooled in a very specific way. That's why they call it dual phase. There's two phases, or complex phases, to the development of advanced high-strength steel. And when you look at the picture that's on your screen on the lower right-hand corner, you'll see that the molecules aren't just packed against each other because they're overly magnified here. They're actually overlapping each other. And the alloys and the bainite and all the things that hold that together, if you heat advanced high-strength steel, those alloys immediately are burned out of the way. Advanced high-strength steel, unheated, has a a yield strength, depending on the steels and the grade, of somewhere around 140,000 pounds per square inch of pressure to pull it apart. Folks, I've been teaching structural repair since 1986. Never seen a machine that could do that. Don't know that I want to use one. It's like that either. So when we see these advanced high-strength steels, we have to understand what the limitations are. It's not that we can't fix the vehicle that has advanced high-strength steel. We just need to know what? How the manufacturer wants us to repair it, or in this case, replace it. As you look at this chart that's now on your screen, what you're seeing here is the trip steels, dual-phase steels, and martensitic steels, and the tensile strengths that they have out into this range. The newer steels, the future steels that you're going to see out in this range as well. Folks, I got to show you some things here that are just actually really, really cool. This is high-strength steel that is a good close-up picture of it. And you can see here where the grains are actually overlapped from each other and how it gets the strength. There's a problem with this, however, if you do this. If you heat advanced high-strength steel, this is what it looks like under heat. There's no way, not any way, that that metal, when it's cool, could return to this state. It is no good at that point. You have an advanced high-strength steel that's super thin and super strong, except for where it had been heated, and then it's been weakened. We're seeing vehicle manufacturers recommend McBrazing advanced high-strength steels on, where there's no actual fusion that takes place. It's kind of like a glorified gluing, if you kind of think of it in those terms. Folks, where are we going from here? I guess I'm going to challenge people that are listening. Type this into your browser someday. Nanosteels. Nanosteels will exceed what we see on normal sheet metal in the next generation. All the steels that we've been talking about are in this category here. And if you look at nanosteels, they are way out in this category. Without getting too carried away with nanotechnology, think of it this way. A nanometer is 1/50,000th the thickness of one human hair. It's hard to get your head around that. 1/50,000th the thickness of a human hair. Put 5 of those together, put 10 of those together, and they have a working guitar at that level. Folks, you can't see it. You need an atomic microscope to see this nanotechnology. Nanotechnology is different than the steels that we're dealing with. I'll just give you a real quick observation. The steels that we've been talking about, they're crushing molecules and binding them together. Nanosteels are like a building block from the blueprint that build from the nano level up. So they're building from a level that you cannot even see up to a strength that duplicates the strength of a diamond and the thinness of the regular piece of paper. That technology is where we might see in 2025 that lightens the vehicle to a point. Oh, by the way, nanosteels can reshape themselves because they're built from a blueprint. I'm waiting for that car. I don't know about you guys. So look that up sometime. You'll find some really, really cool information on steels. And again, that's where we're going. We have to do these kind of innovative things to get to the 2025 goal that year of 54.5 average fuel economy. I like it. Especially for the price of gas. I don't know, maybe even the price of eggs now. So that kind of wraps up our aluminum a little bit here. We're going to kind of focus on, steel. We're going to focus on aluminum a little bit here. Aluminum has such tremendous qualities, folks, because it can be recycled indefinitely without loss of quality. So 2/3 of the aluminum that we already have, it's already been maybe a Coors can or something. Now it's a Cadillac CTS door, where it weighs 15 pounds less, the same door made of steel. It makes a lot of sense to use something like aluminum. Aluminum has some tremendous qualities, as we'll see here. I kind of use this little screen here to kind of show you what we actually have an aluminum class. And this is actually a table of contents out of the aluminum class. So we're going to kind of start here because in the industry we have some conflict between aluminum and steel. What does it take to do aluminum? Is it difficult more than steel? And why is this and why is that? And it creates a conflict, and that conflict is a result of a lack of communication and lack of knowledge. It boils down to that every time. What you'll find with aluminum vehicles most generally, or certainly rather, is the vehicle manufacturers giving recommended repair procedures and very specific procedures. Because if you're going to work with aluminum, one of the things we need to know about aluminum is right there, the alloy. You need to know the alloy of the aluminum you're working with so you can select the right aluminum welding wire. If you don't have the right welding wire, you can't guarantee that you'll have a good weld. So knowing the alloy and the characteristics of that alloy, by the way, alloys are determined by, are determining the strength of that aluminum as well, whether it's 1000, 2000 series aluminum. If we don't know that, the alloys, it can create some real monsters for us. We can work all day long and just beat ourselves against the cement and get nothing done. Because aluminum's different. It doesn't mean we can't fix it, it's just different. It's made different in most senses. You know, the stamping that is done on steel parts, same thing. Put a piece of aluminum in a die, there you go, stamp it out, you got yourself a fender, quarter pound, whatever you're looking for. There's one thing you can't do with the steel that you can do with aluminum is extrude it. Now I have grandkids. My grandkids like that Play-Doh. That's the best explanation I can think of for an extrusion. You put the dough in there and you turn it, and whatever that little die is on the front, it comes out. That's an extrusion. You can't do that with steel. When you have an extrusion, you can build in reinforcements within one piece and not see it from the outside, so you can increase its strength. The other thing is castings. You don't cast steel. Castings you can do with aluminum, but not one manufacturer recommends repairing cast. It's a replace only. Folks, if we don't know these kind of things, it can be a real roadblock. And how do you negotiate that if you don't have the understanding of what the right things are on how to repair aluminum? Not harder, it's just different. Like we mentioned, you need OEM procedures. If you go to an ICAR class, no matter what the topic, what do they say? You need to follow OEM procedures. I'm a firm believer you go right there to start with. There's things that are done that are different in our industry. For some of you that may not know this term of tailor welded blank, they're using 2 or 3 types of metal, welding them together, stamping it, and making a unicide, as an example. So you could have 2, 3, 4, 5 different types of steel, all on the same piece, all stamped into one part. Where do you section it? Can you section it? What can I do with it? Where are those advanced high-strength steels? I don't know. I think the OEM does, though. That's who we need to know about. The other technologies that we're seeing here are laser welding. We've never seen that before. I'll show you if I have time. Laser welding that's so cool and so critical. I got to ask you folks, when you tell somebody, I'm going to return your vehicle to pre-accident condition, do you ever show them your laser welder? Probably not, because we don't have one. So where laser welds on a vehicle, where they're located, you cannot repair anything in that area. You have to section the whole thing. It's getting easier, as you see here, from the original conflict, start helping each other and understanding that these vehicles, how they're built, what it takes to repair that vehicle, and very specific so you don't have some problems there. So one thing about aluminum, it can offer a wide range of variety of properties that can be engineered. And it all comes down to the alloy of it, the temper, and the fabrication process. When it comes to the actual repair, depending on the manufacturer's guidelines, it could have a heat. You could apply heat to do a repair, depending on the manufacturer's guidelines. There's a problem with that. If you overheat aluminum, it anneals. And what anneal means, it's permanently softened. The problem with that is aluminum doesn't change color when you heat it. You can heat it all day long until it reaches a specific temperature of about 3,700 degrees. That's when the oxide burns off of aluminum. When the oxide burns off, you have a problem because you're at 3,700 or so degrees. Way too hot for anything, by the way. So if you're at that heat temperature, you have what's called a big hole where you were heating. Hey, boss, that frame rail, you want me to fix the aluminum? Yeah, it's out there on the ground in a puddle. What happened? I don't know. I was heating it. It didn't change any color, so I kept heating it. That could be pretty critical. You need to remove that oxide before you do a repair so that you can monitor the correct temperature of doing a repair. It's very, very critical. You know, we have a full day class on aluminum, so it's hard to condense it all into this, but things like self-piercing rivet and bonding. You know, a self-piercing rivet with the proper adhesive is 5 times stronger than a spot weld, 5 times stronger than a MIG weld. And the problem with a MIG weld is too many variables, right? It's too early in the morning, I had too much coffee, I got the wrong angle, I'm too far, I'm too close. Too many variables to determine a consistent weld. Ford has changed everything when they came out with the new truck. They were considered of the repairs, and as you see on these outer panels, they've made them so they can actually attach the B-pillar without taking the roof off. Joe, who would have thought of that? This shotgun area up here is easily attached now, where in the past it was hidden behind this pillar right here. So Ford has made some tremendous repairability issues really good for us in the repair industry. They provide the instructions, and the thing of it is, Ford is different than most manufacturers, and they allow you to make the decision of how you want to repair the vehicle, whether you're going to weld it on or adhesively bond it and rivet on. I would suggest getting some training on that for sure. You know, the Audi A8 space frame crashes, we'll take the crash test and pass it like this without any sheet metal on it. That's why it gets a 5-star crash rating. Aluminum can absorb a lot more forces of a collision than steel. This might be an example of a tailor welded blank on the Range Rover. We have several different grades of steel. Aluminum hang-on parts, they have some criteria for that. We're just going to kind of skip that. If it's a stamped part, you determine whether you can repair it or not. But, you know, like we mentioned earlier, aluminum can be formed in several different methods. So stampings, extrusions, castings, and then hydroforming, which we didn't talk about, like the Corvette frame, it's hydroformed. By changing that frame from steel to aluminum, it lightened it up 500 pounds. That's quite a substantial savings that you can put toward fuel economy. I won't bother you with the technology that's in a Coke can because we'll run out of time, but the hem flanges on a vehicle are similar to the top of a Coke can. 3 or 4 different types of alloys in the same Coke can, 3 or 4 different alloys in a vehicle. There's a lot of similarities. The little tab on top that holds the pull tab is an example of a clinch joint, and that's how they hold the hood together. Not like that exactly, but a clinch joint is used to hold together parts of the Ford truck as well. Here's an example of an extrusion, and what you can see is a reinforcement that's built into that extrusion, that inner structure, that honeycomb design. Folks, if you didn't know that was there and say, oh, I think I'll just cut this one right here in section, you got a world of trouble coming because you could no way section a rail in like that. I don't mean to be scary, but many European manufacturers are designing so the front rail or the rear rail would go right inside of that extrusion. So if you have to replace a front rail, you're way back in here into this rocker panel. I don't try to explain how they build them. I just try to fix them like you guys. Well, you're seeing a lot of this hydroforming done where they can condense down several pieces into one. It makes a lot of manufacturing sense. We won't spend too much time on that. But most vehicles have that kind of technology. You know, it's a little different on aluminum, and this is a cool picture if you look at it. I know it's a little bit blurry and probably not the best, but it's off of a BMW Z8. And what's really neat about this is you have all kinds of technology in one piece. So you have a die-cast door frame here. It's extruded beam here, so it's welded together here, an extrusion and a cast. I have an outer skin, and then you have rolled steel that is this reinforcement. All this different technology in one door. What are you going to do to repair it? I have no clue. Who does? The manufacturer. Have to know what their manufacturer's recommendations are. Folks, some of these cars have a little sensor inside of this door that determines the air that is pushed out of the doors as a result of an impact. That door can't even be repainted unless it's stripped down and brought to exactly the same mill thickness. You cannot use filler on that door. has to be metal finished. So you get a little ding in the door that comes in, and oh yeah, I don't fix BMWs very often, but I got one here. I can fix that little dent, bondo it up. Works great till when? Till the airbag in the side deploys incorrectly. Huge liability. We need to know about these technologies. We have some manufacturers that are putting a cast B-pillar. Look at all the ribbing in those areas. It's exactly awesome. No way you could duplicate this. No way you could section it or repair it. It's strictly a replacement. So on the on the Audi A2, the BMW Z8 Roadster, you see those kinds of technologies of castings being used. This is the Corvette. I want one. I don't know about you guys, that aluminum frame. Pretty cool. Let me back up to that, because what's really critical here is this. This is a extruded frame rail right here. This is a cast A-pillar. Listen to this, folks. See if your welding skills are good. You're going to be welding an extruded part to a cast part. I teach welding for a living. I'd have to practice a lot to make that weld and feel comfortable with it. So there's very specific training that goes along with a lot of these vehicles that really, for the technician, it gets us up to the next level of skill. That's where we want to be anyway. I think this is probably one of the better pictures that I could show you, in that it shows a comparison of a body in white. Let me blow this up here a little bit. A body in white vehicle, one, is a steel. And what it's showing on this is the amount of absorption of forces that a steel vehicle would create running into a wall. So that's the steel, and going right underneath it, because this is aluminum, and here's what that really is showing. And this is why manufacturers look at aluminum. It can absorb twice the collision forces of steel. When you can absorb the forces of steel, you can slow down the collision, and you can change the airbag timing, and you can protect the passenger if the vehicle is repaired correctly. And you can see how that makes a big difference between steel and aluminum vehicles. Let me just throw this in real quick for those that like this stuff. Carbon fiber vehicles, if you have this kind of an impact, and normally the forces are directed up through the A-pillar, right? In the carbon fiber vehicle, what will happen at the A-pillar, it will crack at that location, crack right apart. So all the energy from the collision just goes through that crack and out the vehicle. Any other vehicle will go all the way back to the rear of the vehicle. A lot of technology. Again, load pathing. Kind of remember that term. You're going to see it many times in the future, I'm sure. Well, we'll kind of finish this up here a little bit. I think I'm close on time with some joining technology. Because the joining technology certainly has changed as a result of how vehicles are built and how we're going about it. There's a lot of consideration that goes into it. We're not going to spend a lot of time on this. I would love to be able to. We just don't have time. But all the things that go into the selection of the materials, whether it's steel, zinc, aluminum, copper, carbon, whatever it's going to be, all of the decisions of how they're going to weld it, whether it's going to be rivet, bonded, welded, spot welded, friction stir, laser welded, flame brazed, whatever it might be. All of those technologies need to be considered on how the vehicles can be made. One of the things that is forcing us to change a little bit is this resistance spot welding when it comes to aluminum vehicle, because it takes 3 times the amperage that it does with steel. So at this point, there's nothing aftermarket that I'm aware of that you can consistently weld aluminum spot welds. General Motors, as you know, is coming out with a new truck, and they've come up with aluminum welding tips from the factory we can't duplicate. So we're going to be dependent on them to tell us how they want their vehicles repaired. That's coming next year, folks. You need to start getting ready for that now. I'm going to show you these pictures here because this is just, in my mind, a highlight of what we're going to talk about here. As we look at this picture here, these 2 photos right here are an indication of a weld and a poor weld because it's showing microscopically porosity, cracking, and voids, or an expulsion from the weld site. This is what a good weld would look like under a microscope. Why am I talking about that? Well, in the United States, we use what's called a peel test. You have two pieces of metal spot welded together. You pull the top one off, you got a hole in it, and the bottom one has a nugget, right? And we call that a good weld. That is not really a good weld. I'll show you a couple things here. I'm going to show you 12 welds. All 12 of these welds passed the pull test. Only one passed a microscopic test, which happens to be this one. I'm sorry, this one right here. In other words, when Volkswagen, Audi, BMW decides that they want to have a welder that works on their vehicles, they make the manufacturer of that welder tune their welder to duplicate exactly, microscopically, the way they welded it at the factory. And that's what's called a homologation. We don't see that in the United States. That means that that equipment, if you dial it in for BMW and use it as spot weld, it will hit that spot weld every single time the way BMW said, or Volkswagen. I tell you what, that's the quality of a weld when it gets that precise. It scares me to think that all of these welds could go on a peel test and pass it. But on a microscopic test, not even come close. Another technology, just very quickly here, is a laser weld. We traditionally see spot welds here. On late model, ultra advanced high strength steel vehicles, you see laser welding. In fact, you see all kinds of different welding technologies. Laser welding is different, it's unique, it's very accurate, it's very fine, and if you can imagine this in your mind, if you had two pieces of paper and you put them one on top of the other and you could weld through the top piece and you could weld a quarter of a way, halfway, or all the way through the bottom piece. That's precision welding. That is exactly what a laser weld does. We could no way duplicate that in the aftermarket. That is part of, by the way, load pathing. That's where direction of forces are going through vehicles, or those laser welds. That's why we cannot repair those kinds of vehicles that have that kind of technology built into them. I think I'm running short on time, Melissa. You tell me if I am. I would normally show this with video, but it's okay. Thank you.
No, well, you don't have to show the video because you know what, it doesn't really come through very good.
Yeah, and I wasn't going to. But the difference with this laser welding is it's absolutely perfect, absolutely every single time. It doesn't have variables. The photo I'm going to point out right here is the latest technology where you don't see the laser hitting down here. The laser actually comes remotely. I'm going to say that's about a 3-foot distance from where the laser beam is pointing to the surface that it's welding. And had we had time, I would show you this laser scanner welder making 220 welds in about less than a minute. And each one of those welds is a different kind of weld. There's a straight weld, a slot weld, a round weld. All of that is built-in load pathing, built in by the manufacturer. Gee, nobody told us. I don't know how that happened. The other thing that you will see is friction stir welding. Friction stir welding just takes a mandrel and spins it really fast and joins two types of steel or aluminum together. You can join aluminum and steel together, friction welding, or so they say. I haven't seen it yet. The new Honda Civic says that the front cradle is friction stir welded, and it is. The front half is steel, the back half is aluminum, but it's bolted. The friction stir welder that they used welded just the aluminum part of the cross member itself. And then another option for welding for aluminum and plastics are ultrasonic welding. They run at a really high frequency. I know I have some grandkids that wear earphones. I'm convinced that they listen to their music at about 15,000 cycles per second based on the way they act. But in collision repair, that high frequency can melt things together. Ultrasonic welding. Again, we spend a lot of time on this in our classes. Then cold press welding is coming back. That was invented in 1724. My goodness, and all of a sudden we're using it again. Folks, that will kind of end up our presentation for this day. I tried to make it about 45 minutes. I certainly appreciate the attendance, and Melissa, thank you so much for the opportunity. It's just wonderful. So if there's any questions, we'll kind of open it up. If not, we'll go from there.
And I just want to follow up by saying that I'll send everybody who's attending this webinar Ken's contact information. So if you do have questions, you can follow up with him. I don't see any here. If anybody has any, go ahead and type those in, and he'd be happy to answer them.
Yeah, just don't make them hard.
Okay, well, I think that'll wrap up the webinar today. We appreciate everybody joining us, and we'll be in touch with future training opportunities. Thank you, Ken. And again, we'll send everybody your information.
Thank you, Melissa. It's a pleasure.